Hi, I'm Jay Richards, and we're here at the COSM 2021 conference talking about the future of technology. I'm joined now by Julie Love, who works on quantum computing here in town at Microsoft. Julie, good to be with you.
Great to be here.
Yeah, so just enjoyed your talk on quantum computing. And so for people that don't follow this, I mean, this is your world. In fact, you did this in undergrad and graduate school, you described that. But what exactly is quantum computing for the uninitiated?
Yeah, quantum computing is going to be a new, what we call a coprocessor to classical computing. So, and it uses really different building blocks than classical computers. So if you think about a classical bit, it's 0 or 1.
Mm-hmm.
You know, these tiny transistors that are in our watches and our phones and our computers. And quantum computing offers us a different building block where quantum speaks the language of nature, and instead of just 0 and 1 with the bits, they can be in superposition state and be 0 and 1 at the same time. They can be entangled together. So we could have 2 qubits here entangled together. You could take yours back to DC or even to the other end of the universe. And something that I do here locally on mine instantly affects yours. And so these are really different building blocks. And with that, we can come up with new algorithms to solve problems. And certain classes of problems with these new building blocks can be solved exponentially faster. So that's why we're really excited about it and invested in this technology.
Well, and so you talked about these different sorts of algorithms, and something that I think is an important distinction is that you're developing algorithms, and that's actually preceding the development of quantum computers that can actually run them. Is that right?
Well, we're really doing both in parallel. This idea that quantum computers would exist was proposed by Feynman and others already back in the 1980s. And so there's been, in advancements in the quantum, what we call quantum information science since then, and really exciting algorithms proposed in that time frame. And I think this is where it's different evolution from classical computers, right? We had the hardware, and then we had to figured out what to do with it. And that knowledge of how to write code, how to do resource estimation, we have these powerful tools that come out of our knowledge of classical computing so that we can advance the state of the art in algorithms even before we have the hardware. And so that's really exciting. And it's also really important, as I talked about earlier today, is really understanding that use case allows us to understand what's required of every layer of the stack. And so by understanding the algorithms and what's possible, then we can say, okay, how many qubits do we need? What sort of gate speeds do we need? How much information flow is going to come, up and I'm thinking about it very vertically because it's these physical systems, and we have the quantum, the quantum hardware sitting at the cold stage of one of these cryogenic systems that really is kind of, up and down this full compute stack, but that information is critical because that allows us to then build the technology we need to realize the algorithms.
So where are we on the hardware side at the moment? I mean, I've been sort of following this, superficially, maybe for 20 years, and very often people were saying we're a year or two away from some major breakthrough. But where would you say we are right now in 2021?
So I would say, still in the early stages. The state of the art on quantum hardware is sort of tens of qubits. These are pretty noisy systems. They need a lot of error correction. Quantum computers can still have errors, and we can correct for them, but that works really differently. To get to where we need to be to solve interesting applications, maybe 30,000 qubits for scientific discovery, but as we think about economic impact and designing a new catalyst to say to remove carbon from the air, we're in the millions of qubits range. And so that's where we need to, we're at the starting point with this technology, and we need to have a scalable system at every single layer of the stack to realize that. Okay, so something that was a misconception, and I think is at least vaguely in my own mind, and I know it's a popular misconception, is, well, quantum computing is it's going to be this thing that's going to come online, and it's going to transform all computing, and it's going to make the old classical way of doing things obsolete. It's going to replace it, and all the encryptions are, everything's going to get exposed. But you said, no, that's not really right, that there are sort of classes of problems in which quantum computing is going to work, and there are other ones for which classical computing makes sense. Kind of unpack that a bit. Yeah, absolutely. So it's not going to solve everything. And just at the heart of it, if we compare what a quantum computer could do in the future with the classical, state-of-the-art classical processor today, all of the relevant timeframes, so the speed, so you think about read, write, the I/O speed, getting data in and out, probably about 10,000 times slower.
Okay.
The clock speed, orders and orders of magnitude slower. And so for kind of general purpose computing, you're much better off using classical computers. They're readily available, scalable in the cloud, elastic capability. And it's really for those compute-bound applications where you need that speed up. And so we can counteract those speeds all being orders of magnitude slower if we have an algorithmic speed up that outpaces that.
Okay.
And so, you get, that if you get an exponential speed up, you can handle the slowdown on the clock speed. And so it's, really at this point in the technology, it's looking for those areas where we have, more than quadratic speed up and not a huge amount of data being read in and out of the system. That's going to be the sweet spot.
Okay.
And those are applications in chemistry and material science.
I see. Okay, so do you think that's where the most exciting applications are, or are there another?
Absolutely. Those are going to be the first applications that we're going to see. And even if they're the only applications that we see for quantum computers, it changes everything.
Absolutely. I mean, materials, whether you're talking about carbon or new forms of energy or whatever. Yeah, it is absolutely exciting. So sort of venture guess, and I'll give you a wide time sort of frame. So in the next 10 to 25 years, what would you expect something to see optimistically?
In that time frame, absolutely transformational technology. This is, one of the things I closed with during my talk today is, as you look at technology that scales exponentially, and quantum really does, when you every time you add a qubit to the system, you double the computational power. And so these technologies always start out and it looks very slow, and it accelerates rapidly as we build these scalable systems. And we're really excited to put this in people's hands and see what they're going to do with it.
So we're still somewhere along the sort of horizontal line of the exponential
the early
curve.
stages of that exponential curve.
Yeah, so it'll be exciting. Let's be sure to talk when we're in that bend at the elbow. Well, Julie Love, it's great to be with you. Thanks for joining us.
Great to be here. Thank you so much.
I look forward to talking to you at a future COSM conference, actually.
Sounds great.
Yeah. And I'm Jay Richards. We're at COSM 2021. Thanks for joining.